working. Let's see. 1 2 1 2. We're testing. But there's no mic. But let's just pretend there is. The camera's focus like a piece of shit. Focus on here. Okay, let me just say. Okay. Please just like, why are you stupid? Focus. Is it retarded? One watching. I don't know if that's me or not. Can you please? I want to click all of the animation. Yeah. Boom. Nope. Please. Oh. Okay, let me just pop to the chat something. One other 3, and this is still not working. It's a little bit annoying. Focus on the marker. Oh, nice. Welcome. What do? Okay, we're gonna start soon. Don't worry. This is gonna be perfect. Welcome, Alia. This is gonna be a good live. This is gonna be a good one. Don't worry. I know this is gonna be a good live. I've actually prepared for this one, so I know it's gonna be good. Give it 3 minutes and then I'll just start. I don't care. People can watch this later when I upload it. Okay, only 2 more minutes and then you gotta start. Oh, why does it stay focused on the text? There you go. Nope. Okay, I don't care. Whatever. Okay. Let's make a start. Yep. It says there are 3 people here, but I only know of 2, so I'm gonna assume that there are 2 people here. So, okay, now we're actually starting. So, these functions. When we think, okay, also, by the way, this video will be a bit different because I'm in a new room, so I don't have the whiteboard, so I'm doing this on the table. So, yeah, this is how I'm doing it for now. So these functions, let's go something like okay, great start. Let's get into this. Okay, let's go into this. No, actually, I don't want to get this because this isn't important. This is important. Okay. So functions. The screen can stay unfocused. I don't care. Okay. So functions. What are functions? Let's start from the beginning. Okay. Before, let's just everything you know about functions up until now. And if you're here, it's probably because you don't know anything, but that's fine. Everything you know on functions up until now, just like forget it. Just don't know anything about functions. Like if you're watching this, like just forget everything about about functions, because it's probably 90% of it is like wrong. So when we think about functions, okay, there are a bunch of ways of thinking about functions, and you can do it the way that schools do it, which is just telling you what it looks like on a graph and how to draw the graph, or you can think about it in a way of understanding. Exactly. That's what we need. What even are functions? That's the first question, okay? What are functions? Because before we know what they do, before we know how they work, before we know why they even work or why we use them, we need to know what they are. So, what are function? What are function? So, let's think about it in this way, okay? Pretend now you failed school and stop fucking focusing. Okay, you failed school now and you've gone to work at a factory. You do you screen. You've gone to work at a factory, okay? And you go and they put you in charge of a specific machine. This specific machine, which takes in something and gives you out something, right? And you want to know, so this machine that they've put you to work on, it only works with numbers, okay? So don't try putting like pizza in there. Promise you, you could put pie, but pizza won't work. So they've put you in charge of this machine that takes in one thing and does something in the middle and gives you another thing on the outside. So now, the question is, how do we show what this machine does in a way where we can understand it? So every machine like this has you can put in one input and it will give you a unique output for that input. So every input has only one output. Now what's important with this is that it doesn't say that outputs have only one input, but every input has only one output. So right now, because you don't know anything about functions, remember, you don't know anything, doesn't even make sense. But it'll soon make sense. So, what these functions do in maths is they manipulate numbers. And how we write them is not with a box and a bunch of arrows, but normally with the letter F for function. I don't know why I use the letter F, but it makes sense that it's for function. With the letter F, and then a bunch of brackets, and some variable in the middle, and then that's equal to something. Now what this fx thing situation does here, it's telling you that this function, when you put something into this function, you replace everything that's inside the function that has an x in it with that input. So let's say our function is f of x equals x. Just that. Very simple. That means that whenever you put a number into there, into there, it gets put into here, and then whatever the answer is for here gets thrown back out. So let's say we had, this was f of x, this is our function, and we have, let's say, f of 2. All we do is replace all the x's with 2's, and that's our answer. Mind blown. Okay, now that's pretty simple, and it's also very oversimplified, but that is what a function is, and this function right here is something you're actually getting tested on in the test. And if you think about it in this way, it's very simple. And the one thing to understand with functions is functions aren't graphs. A graph is this, a function is this. This is a function. That was a graph. They're two completely different things. But what we can do is we can use graphs to visualize functions. But functions are not graphs. Okay, now that you got that in your head, and that functions are not graphs, and these functions things, all they do is they take in an input, they do something to that input, and they give you an output, we can start thinking more in detail about why we use functions. And if you also, once again, if you have any questions, just put them down there in those comments area. Probably won't see them because I'm not really concentrating on that, but I'll try looking and I'll try to find it. Okay, so now we understand what functions are and what they do. They take an input, they manipulate that input, and they give you an output. Let's think about why we use functions. Oh, the camera's like dying, it's fine. Why function? Why do we use functions? Well, so we've already said, we use functions to manipulate numbers. But why does that help us? Why do I need to use one function to manipulate numbers? And the answer is that it helps us to predict and estimate specific things in specific scenarios. Focus. Thank you. Nope. In specific scenarios. So let's take an example, right? Where we use functions to predict or to estimate a specific answer for something. Let's say you're a pretty lonely person and you have an Instagram account and you post one post on there. This is one post. One circle is a post. And you only have 2 people that see that post. Only 2 people that see that post. But what they do is they're so kind that because they saw the post, they decide to share it as well. But because they're also lonely people and lonely people have lonely friends, they also only have 2 people that see the post, each one of them, and those 2 people once again decide to share the post. So every one of these circles is your post being seen by one person. So here, here, your post gets seen by one person, which is yourself. Here your post gets seen by 2 people, the people that shared it. Here your post gets seen by 4 people, the people that saw the people that shared. And this carries on forever. Forever and ever and ever. Every single person that shares your post, sees your post, shares it to 2 people. These are connected. Now what is this? How does this have anything to do with a function? Right, let's think, okay? What if we ask the question, after 5 times your post got shared, how many people saw it on that 5th time? Okay, well I have to think about this logically now. Let's try break apart the problem. Let's first see how many times our post gets seen every single layer. And this isn't really a good representation because it's more like a circle than a layer, so let's just redraw it. So the first time, and you can see it's right there, like right in front of your face. The first time when your post gets seen, one person saw it. The second time where your post was shared by 2 people, 2 people saw it. And then 4, and if we count here, 1, 2, 3, 4, 5, 6, 7, 8 people saw it. And by here you already see the pattern emerging, that every single time your post, the amount of people that sees it gets doubled. So here it gets doubled, and here it gets doubled, and here it gets doubled. Not x, times. Okay, so now you're tempted to say, fine, I know functions, this is definitely y equals 2x, because you see 2x, 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 2x. I'm smart. Remember what I told you? Forget everything you know about functions. Because this, if you think about it logically, is not 2x. Because if we label each one of these rows as a number, let's call that number P for post. There's P1, P2, P3, and P4. What you notice... Oh, sorry, no, this is wrong. It's not like this, it's like this. P0, 1, 2, 3. Why we start at 0? Because at this point, your post hasn't been shared yet. So only one person sees it, which is you, because it hasn't been shared yet. So the question is now, after Pn, how many people have seen your post? And the answer is, if we look at it at 0, the answer is 1 for 0. And what we can see is that your post gets doubled. And that the amount of people see your post grows exponentially. And this is one example of a function. Because what we see is that your answer is that how much is your function growing? By 2. And because it's exponentially growing, we'll have to say it's put in on the top there. And this is an example of a function because we get f of x equals 2 to the x. How we got to the function isn't important. What's important is noticing why we used a function to figure out the growth. And functions are normally related to growth. Growth and functions are like tied hand in hand because they're very similar. You use functions to display growth. So now that we know why to use functions, why we use functions, what are functions, these weird things that take in inputs and outputs, let's see how many functions there are. How many functions we can think of and how many functions we can use. So, if we think about this, a function can be anything as long as it manipulates a number and uses this variable. F of x equals x. That's a function, right? And this is also a function. And this is also a function. These are all functions. What can we deduce from this is that we have an infinite number of functions. And that doesn't help us. We need to find a way of categorizing these functions, of putting them into categories which help us understand them better. Okay? So, what categories are there? Let's think, okay? We can have, if we think about growth, of all the different growths that we have, we do have the most simple growth, which is, well, actually, let's start from the beginning, which is no growth. When nothing grows, it means that it stays the same. But this is representation on a graph. We don't care about graphs yet. Graphs, because graphs aren't functions. Graphs are just ways of visualizing functions. Meaning that, let's take an example of linear growth and see what we can deduce from it and what linear growth is in a function. Let's take an example of this. You're in a parking lot. And this parking lot is infinite. And it goes on forever. And then we can give these parking lots spots or names. We can call this spot 1, spot 2, spot 3, spot 4, spot 5, spot 6, all the way to infinity. And each one of these spots, we have a car. And that is a great car. And these are the cars of the future. So, deal with it. And what do these cars do? Every single car has got one person driving in it. We want to know, after, let's say, 6 spots, how many people are in the parking lot. Well, we can count. We can say 1, 2, 3, 4, 5, 6. There's 6 people after 6 spots. After 5 spots, there are 5 people. After 4, there are 4. And we can say after 30, there are 30 people. Meaning that for every spot of x gives us x people. And this can be written as a function, because you can use any letter, meaning Sx equals x people. But what if all of a sudden, every single person in these infinite cars, without even a partner, had a baby? And we have one more person in every car. All of a sudden. That means that after one car, you can focus, you do you. After one car, we have 2 people. 2 cars, we have 4 people. 3 cars, we have 6 people. And you see, it grows. But the one thing that we notice here is that the growth rate, or the distance, the gap between every single number stays the same. At the beginning, we had 1, a gap of 1. Then, we had a gap of 2. And if we had 1.5 people in every car, savages, we'd have a gap of 1.5. And that is what defines linear growth, that the gap stays the same throughout the entire function. Or when you apply the function onto the numbers, the gap stays the same. Now, what does this give us? What function does this give us? Is instead of having 1 person in every car, we have 2 people in every car. Well, once again, you'd be tempted to say that it's just x plus 1. But that's wrong, because we're not adding 1 person at the end of it. We're adding 1 person for every car. Meaning that if a car is this is actually 2x. Because we have 2 times the number of cars. And if we were to see this graph, like visualize it on a, if we were to visualize this function as a graph, we'd go here and we'd see that this is a graph for y equals x, or for f of x equals x. And we can see we have here ax plus b, and a equals 1 and b equals 0, meaning it's just a normal y equals x graph. Now to make this into our function, we can just make a 2, and we get that it's a little more slanted upwards. But as you can see, it's still linear because every single gap is even, or is equal. So let's go back now and see what happens to this graph as we change a and b, and how the function influences the x-axis. Now, one thing to understand about functions, oh, you can't see my hand, that makes sense. Okay, one thing to understand about functions, and the main thing about functions, is that we said that a function, that a function takes in an input and gives us an output. Let's say y. Uh-oh, that's off. Great. Probably gonna fuck up everything. I didn't. Okay, so every function gives us an input, or we give it an input and it gives us an output. And this is true from what you do know about functions, is that f of x equals y. But what we can say is that when we apply a function onto this number line, this real number line, which means we've got 0 here, and these are all the numbers, the real numbers, all the way to infinity and negative infinity. When we apply this function onto this graph, there are different ways of visualizing it. And one of the main ways of visualizing it is by adding in another plane that also, a real number plane called y, and we can call this x and we can call this y, meaning this is our input and this is our output, and we can graph where every single input goes to our output. So if we have the function f of x equals 2x, all we can say is that when we put 1 into here, we get 2. And when we put 2 into here, we get 4. Hopefully that's right. Yeah, that's right. And when we put 3, the next input, into here, we get 6. And what functions do is what graphing functions does is it tells you what happens when you put every single input into this function, and it shows you the output for every single input, which would be something like this. Or not really, but still. So what graphing a function does is it asks, where does every single input go? And show, put every single input into this function and show me where its output is. And then normally there's so many inputs, there's so many tiny little inputs here that it looks like a straight line. But really it's lots of little inputs. And that gives us a line. So this input goes here, this input goes here, this input goes here, this input goes here. And it's tiny little dots, but there's so many of them, literally like an infinite number of them, that it gives us a straight line. And so from that, we can look back at our graph Okay, so from here we can look back at our graph and we can see what A and B do to the graph as they change. So we can press play here and we can see what A does as it increases and as it decreases. So, okay. When A increases, you can see that the graph gets higher and higher up, or more vertical. And as A decreases and approaches 0, it becomes more horizontal. And then after A becomes negative, the graph flips over. And this is only affecting A between negative 10 and 10. But as you can see, as A approaches infinity, the line basically becomes vertical. And then as A is 0, the line is horizontal. And then when it's positive, it's facing this way, and then when it's negative, it's facing the other way, which is just like this. Okay, let's put A back at 1. A back at 1. And let's see what happens to B as we change the graph with B. We're looking at this graph right over here now. Looking at this graph here. What happens to B as we change it? What happens to the graph as we change B? Well, we can see, oh, yeah, you do you. The graph starts moving up and down. But what moves up and down? The entire graph moves up and down, but what changes is the intercept right over here, the y-intercept. The output of the function when we input 0. That's what changes. And it makes sense that that's what happens. Because if we go back here to the beautiful table that I have here, if we go back here, we're asking, what is the y-intercept in reality? The y-intercept is what is the output when the input is 0. So if we have this graph here, the y-intercept, if we input a 0 into there, we get 0. But what if we have a graph like this? To 7x plus 5. And if we input 0 into here, all we get is this 5. Because the 7 becomes 0. And that's what B in this example here, that's what B is. It's literally just giving us B as the y-intercept because A is 0, because x is 0. Because we're inputting 0 and we're looking for the y-intercept. And that's only one type of graph. Now that's the linear graph. Let's move on to a little bit of a harder graph to understand intuitively, but a pretty easy graph to get from like looking at the graph itself, but it's a function, it's not a graph. So let's move on to the next type of category of functions. So let's label our categories. We had our linear, and that's just our x. And you can write it out in full if you want. We can have mx plus c, ax plus b, ax plus q, whatever you want to call it. I'm just going to leave it as a and b, ax plus b. Our next sort of category, and we want to discover these. We want to just know them. We want to discover them. Now let's think. What was the exponent here? Well, it wasn't 0. I'm just asking what was the exponent. Don't put a question mark. It's better. What was the exponent here when we were using this graph? Well, it was 1. Now we can ask this. Let's be curious. What happens when we increase that exponent there? And not increase it by a factor of x, just increase it to another number. What happens when this exponent is not 1? When this exponent here is not 1. And in grade 10, you only learn about it being 2. But by the way, functions, there are an infinite number of them, and every single function is just a function of x. So you can have functions where the top number, the exponent, isn't 2. Please focus. Where the exponent isn't 2. It could be much higher, or even much lower. And it is at some point. So now we're asking, what happens when the exponent is 2? Well, we can think about this in an intuitive way first. Okay? Let's say you own a company, a cookie store, and you want to attract customers in. So you give them this deal. You give them this deal. If you come with a group of X people, I will give each person X cookies. That's the deal you offer them. And it's in the two options here. It's either you understand the deal or you don't understand my handwriting. But that doesn't matter. So this is the deal you offer them. But what does this deal mean? It means that if people come in with a group of, if you come in with a group of 5 people come in. That means that each person, let's just draw them as a little stick man. That means that each person, all 5 of them, gets 5 cookies each. And if you have a group of 4 people, or of 2 people, that means that each person gets 2 cookies each. Meaning, if you want to have a party, and you want lots of free cookies, come to this place and invite like 50 people. You'll each have 50 cookies. Each person will get 50 cookies. Now the question is, for every number of people, how many cookies should I be making? And let's look at the 5 now. Okay? We have 5 people, and each person gets 5. Meaning that we have 5 people times the 5 cookies that each person gets, and if we simplify this and not get the answer, just simplify, we end up with 5 squared. And if we had 2 people, each person gets 2 cookies, so it's 2 times 2, which is 2 squared. Now what's the correlation between both of them? It's the number of people, x people, means you have to make x squared cookies to account for those people. And so now, if we want to visualize what this does to a graph, now that we understand what the function does, if we visualize what happens to a graph, we can go to, let's just erase this whole thing, to this graph right here. If we go here, and we can see that we get this graph, and b has to be 0. Okay, and we get this graph here. Now, what does this graph show us? It shows us that the more people you invite or bring to the store, 1 person, 2 people, 3 people, 4 people, 5 people, you'd have to make that number of people squared cookies. So if you bring in 1 person, they only get 1 cookie. Easy. If you bring in 2 people, each person gets 2 cookies. So you have to make 4 cookies in total. And if we, let's say, zoom out, we see that by 50 people, it's already nearly impossible to see that many amount of cookies. It's somewhere up there, and it's a large number, but it's there at the top somewhere. And this function we call a parabola, but it's just a quadratic function or an x squared function. And all it means is that for this input, we want to make this number squared output. And so the function, if we look at it here, if we look at the function here, go away. Oh, okay. F of x equals x squared. That means when we throw in something in there, it gets squared and it comes out. Now the weird shape of that parabola has is due to the fact, firstly, because it's a function with a number bigger than 1. But what the squares does is if we explore what the square does, we can check what happens if we throw in 5. We get 25. Pretty simple. But what happens if we throw in 0? Then we get 0. And then what happens if we throw in -5? Well, what happens to -5 is it becomes -5 squared, and a negative number squared becomes positive, so it's 25. And that gives us a weird solution. Thank you. You can stop focusing now. And this is a weird solution because what it's telling us is that whether our numbers are negative or positive, our output will always be positive. And if we look back at the graph now, we see that it's true. For all the positive inputs, we get positive answers. And for all the negative inputs, we get positive answers. And if we see what happens to this graph when we change A, as A increases, then as A decreases, the numbers become smaller and smaller, and when A is negative, the graph just gets flipped over. And as A increases and goes back to 0, the graph is horizontal, and then as A increases again, and as A gets bigger, the graph gets thinner and thinner, and as A approaches, well, gets close and close to infinity, the graph just becomes a vertical line from 0 to infinity. Okay, let's see what happens to the graph as we change B. What we can see is that the graph moves up and down. Bye-bye. And then it comes back. Now, why does this happen for B? Oh, it's always actually -1. Why does this happen for B? This happens at B for the same reason that it happened for the y equals x graph. What we're asking is, when we throw in 0 here, what answer do we get? And we get either 0, but if there's a +1 here, then we get 1. And if there's a 2 here, then we get 2. And that's why B, or the y-intercept, is determined by this number there. So we've looked at x squareds now, and the next graph or next function we can look at is a function that's really hard to explain. It's this function. The 1 over x function. And the fancy name is the hyperbola. It's really hard to explain because understanding it intuitively without the maths is hard. It doesn't come up a lot in everyday life because fractions don't come up a lot in everyday life. So let's think about this now, okay? Let's get another example to try and understand it, just to try, okay? To try and understand it. And the example I'm going to show you now is not an exact example of what's going on. It's more just understanding on a smaller scale of what's happening in a bigger scale. So, you have 50 people in a class. And at the beginning you start off with 25 boys to 25 girls. So it's all equal, and it has to equal 50. The class has to have 50 people. Now a question we get asked is, what happens if we increase the boys by 1? So we get 26 boys. Because the class has to equal 50 people, the girls must be 24. We add 1 to the boys, we take away 1 from the girls. This relationship you get going here is as one increases, the other one decreases, and vice versa. So if we take it now to a better example, we can look at a scale. Can look at a scale. There's a scale. Right now the scale is even. Though, as we push one side downwards, and then gets pushed down to here, the other side needs to get pushed up to there to balance it out. And so what this shows us is that as this number gets closer and closer and closer to 0, this number gets bigger and bigger and bigger and bigger to infinity. And as this number gets bigger and bigger and bigger to infinity, this number gets smaller and smaller and smaller to 0. And if we see this in a graph, then it's easy to understand, because this is one of the things that seeing it as a graph is easier than seeing it just as an example. Here's the graph for 1 over x, y equals 1 over x graph. A is 1, b is 0. What we can see here, if we look at the inputs, is that as our x gets bigger and bigger and bigger and bigger and bigger, our y gets smaller and smaller and smaller and smaller and smaller until it approaches 0. Because as x becomes like very close to infinity, y gets very, very close to 0. That's what we call an asymptote. It's when one number gets so close to infinity that the number approaches a different number so that it might as well be that number. And the same thing happens here. As x approaches 0, or gets really, really close to 0, y gets really, really, really big. And it's the scale thing where the one moves up, so the other one moves down, and the other one moves up, so the other one moves down. And this function is really confusing to explain normally. And so what I recommend for the 1 over x, or for the hyperbola, is to just know it as it is. Obviously to understand the fact that it's a relationship where one goes up, one goes down. Same thing here in the negatives. As the negative goes up, or as this negative becomes closer and closer to 0, so it gets bigger, this one gets smaller, and as this one gets smaller, this one gets bigger and bigger as approaches 0. Remember? Because going up to 0 gets bigger, this gets bigger, smaller, and smaller. So what we can see here is that what we get is, and why does it not meet at 0? What happens at 0? Well, we ask this question. What over 0, what does 1 over 0 equal? Well, it's undefined. And this makes sense because the graph kind of splits at 0. And then 1 comes in there, and it makes a loop all the way around, and it comes in from there again. And it makes sense because at 0, the graph is undefined, because you can't divide by 0. And what happens when y is 0? Well, that means that, once again, when y is 0, we want y to be 0. 1 over what gives us 0? Don't say 0 because that's undefined. It's actually, as the number gets bigger, as the denominator gets bigger, as the denominator gets bigger, the overall number gets smaller. Which means that only when x is the biggest number possible can y equal 0. And what is the biggest number possible? Sure, Alia. Well, what does it mean when this number gets as big as possible? It means that the biggest number possible is infinity. It's not a number, but it's a concept. And it's the concept of the biggest number possible. And if we put the biggest number possible into there, only then will we get 0. And that's why on the graph we can see that only when x approaches the biggest number possible, which is going that way, does y get closer and closer to 0. Okay, and that's the hyperbola. The final graph which you're going to learn, for paper 1 at least, is the graph we've already looked at. The first example we did, which was the exponential. This graph has 3 different... Oh, we didn't even look at what happens to the graph with A and B. Let's go back. Let's take a step back quickly. What happens to the hyperbola once we change A and B? Well, let's look. When A changes, what we can think of is the scale moving, the arms of the scale getting longer and longer and shorter. And then once the scale is positive, it's this way, and when it's negative, it just flips over. This is once again one of the harder graphs to explain intuitively because it doesn't work that way. But just know that when a gets bigger, it gets further and further away from the origin, and as a gets smaller or closer to 0, then it gets closer and closer to the origin. And when a is 0, it's just like a little cross on the origin, because everything is 0. Anything over 0 is 0. And let's move a back to 1. And let's see what happens to b as b. Let's see what happens to the graph as b changes. What we see is just as always the y-intercept changes, or the asymptote changes, or we can assume that it's the y-intercept. And all that it does is, well, it's kind of lagging, but whatever. What we can assume is it's just this area here, when x equals 0, which it can't, because x can't equal 0, the area where x is supposed to equal 0 moves up and down with it. That's what happens when we change b. If we make b 0 again, this is what we get. Now let's move on to the final graph, the graph that we've already done, we've already looked at, but is still good looking at it again, is what happens when we have a normal base, we can call it a normal base, to the power of x. And we've already looked at an example of this. The example is just the one with the posts at the beginning that we did. So we don't do another example. But what's important to know about this graph is that this is exponential graph, and that as x increases, the graph becomes bigger and bigger and bigger and bigger at a rapidly increasing rate. And as x decreases, thank you, you do you. As x decreases, this graph becomes smaller and smaller and smaller, and even when x is negative, when we have negative x at the exponent, it's the same thing as saying 1 over c to the x. So what this shows us is that even when x is negative, it gets smaller and smaller and smaller and smaller and smaller, this number, because this number is going to get bigger, but because it's 1 over that, it's going to get smaller and smaller and smaller until x is either negative infinity or positive infinity, and then the answer is either 0 or positive infinity. So because we already did an example, we don't look at another example, but if we go back to the screen here, we can look at this graph, and this is how it looks when a is 1, when b is 0, and c is equal to 2, so the base is 2. Let's first look what happens when the base changes. As the base changes, the graph just becomes, the rate of the growth of the graph just increases, and the base cannot be negative. Let's take a look at that. So all we know is that for a positive base, the rate, just as the base gets bigger, the rate of growth increases. As the base gets smaller, the rate of growth gets smaller and smaller and smaller until the graph starts flattening out. And at 0 it's 1, because we have 1 times 0 to the power of anything. I wonder why that works. Oh no, sorry. When c is 1, then it balances out at 1, which 1 to the power of anything is 1. And then as it gets smaller and smaller and smaller, the graph flips over. So anything between 1 and 0 give us an opposite graph. And then when c is 0, it's just nothing, like a flat line. All that puts 0. And then when c is negative, we get nothing. Let's look into that. Let's look into why when c is negative, we get nothing. We're asking what happens when c is negative. What happens when c is equal to a negative number? So it's when c is less than 0. We're asking what happens then. Well, the answer would be, if we look at it, though let's say c is equal to negative 1, what we get is negative 1 to the power of anything. and negative 1 to the power of 2 is fine. That's equal to 1. But what happens when we get to negative 1 to the power of negative 2? Well, not even that. Negative 1 to the power of a half. Because that's possible. That's definitely possible in this situation. What is something to the power of a half? What that means is the square root of that number. And what is the square root of negative 1? Well, as far as this number line is concerned, nothing. As far as this number line is concerned, the square root of negative 1 equals nothing. And if you want to know what the square root of negative 1 equals, then stay tuned for like another episode on complex numbers. Another live stream on complex numbers, which I'll do later for the 8th maths exam. But right now, the square root of negative 1 equals nothing, which means you can't have C be negative, which means that this doesn't work, and this doesn't work, and this doesn't work, which means that C cannot be less than 0. C is not allowed to be next to 0. Let's go back to the screen now and see that because C is less than 0 right over here, doesn't work. And as soon as we lift it up, back up to be above 0, then we get our beautiful graph back. As soon as we make C2 again, which is a very nice number, like organic, I don't know if it's, yeah, nice. Actually, the most organic growth is this one. That's the most organic growth. And you can see over here what E equals, this number here. That is the most organic growth. It's literally natural growth. It's how things grow naturally using this letter. That's what E is. E is the rate of natural growth. And it's 2.71828182846, that number. Strange number. Not going to remember it. But yeah, that's the most natural growth. Let's put it back at 2. And what we see now is that this is what happens when C changes. The rate of growth changes. And when C is between 0 and 1, the graph flips over on the y-axis. What happens when A changes? As we can see, it's not the rate of growth changes, but the overall, the rate of growth stays the same. It's just where the rate of growth happens along the x-axis changes. The rate of growth is still the same, it's just where it happens on the x-axis changes. And then at some point, the graph just moves downwards, and it flips over when A is negative. Let's move A back to 1. And let's see what happens when B changes. Same thing as all the other graphs, just the asymptote or the y-intercept just moves up and down. And I've already explained this a bunch of times. What happens is because x becomes 0, and the only thing that's left behind is the constant at the end, which we call b right now. But you can call it c, you can call it q, you can call it whatever you want, and that's the reason. If you don't know what happened, you can look back into the video and you can see why this happens. This makes b back to 0. And these are the 4 categories that you're going to need for the test. The linear graphs, your quadratic graphs, or your parabolas, and then your hyperbolas, or your inverse graphs, and then your exponentials, which is your something to the power of x. And then finally, what we can look at the end are inequalities. Inequalities with regards to these graphs. Let's move back to a normal parabola. Now we want to ask, let's move back to the camera. We want to ask now, if we have this graph, we want to know when in this graph is x greater than 0 in this graph. When is x greater than 0? Now, you can do this in many ways. you can check using a graph that you'll have with you, or you can calculate every single number and spend your entire life doing it. The easiest way is to do it with the graph. So if we move back to the screen, once x is greater than 0, and remember b was 1. B was 1. We want to check when is x greater than 0. Therefore, for what values of y is x greater than 0? That's a better question. For what values of f of x is x greater than 0. And if we go back to the screen, what we can see is that when we look here, for which values of y is x greater than 0? So these are the values of y across here. Values of f of x, values of y, same thing. So what are the values of f of x? So when is x greater than 0? From here all the way to there, to infinity. Meaning, which of these values over here are these numbers bigger than 0? And we can see that. It's from 1 all the way to positive infinity. That's when these graphs, these values here are greater than 0. And this is what I said at the beginning, when I mentioned that for every single function, there is one unique output per input. But for every single function, there isn't one unique input per output. Because as you can see here, we have the output 2, let's say. And in this case, for the output 2, y equals 2, there are 2 inputs. It can be -1 or it can be 1, which gives us the output 2. And that's what I said about the functions having one unique output per input, but not one unique input per output. And this is why this question here, I'll go back here, this question here will not be asked. For what values of f of x is x greater than 0 is wrong, because there can be multiple values of x where f of x is greater than 0. Where there can be multiple values of x that correlate to the one f of x point, and that's not necessarily what's going to happen. So a better question is, for what values of x is f of x greater than 0? And the question here is, and the graph for this is this one over there, the graph for this one here. So we get that the answer is for what values of x, which means which values here correlate to where f of x is greater than 0. Where is f of x greater than 0? Well, here it's greater than 0. Actually, it's everywhere greater than 0. It's greater than 0 everywhere. Meaning that the answer is that for every single value of x, f of x greater than 0. Therefore, we can just say x is an element of real numbers. Because for every single input of x, this graph is greater than 0. We can try a different question now. For x squared minus 3, which part of the graph is less than 0? X squared minus 3. X squared minus 3. Which part of the graph is less than 0? So if we come here, we change b to -3. -2.7, no, -3. -3, we get this graph here. And we're asking, for what values of x is f of x greater than 0, less than 0? Meaning we only want from here all the way to here. That's where it's less than 0. That's where the y values, f of x is equal to the y values. That's where the y values are less than 0. And we can see that it's not equal to, it's not less than equal to, it's just less than. So it's from this point here to this point there. And the 2 points are on the screen right now, negative 1.732 and 1.732. But if you want to calculate them, then all we can do is come back here, and we want to see where find the x-intercept of this is. So we're going to come here and find the x-intercept, so we let this equal 0. Let's just leave this here, but I don't need all this stuff. We want to find where this equals 0. Well, 0 over there. Where does it equal to 0? Well, we can say x squared equals 3. X is equal to plus minus square root 3. That was a little bit of quick algebra there, and everyone should be able to do this. If you can't do this, then you can hit me up and I'll help you. And so all we did here was move the 3 to the other side, we let it equal 0, and then we just square root of that 3, and it's plus minus because there are 2 answers because it's a 2 over here. Hint, hint, wink, wink. And now once again, let's move back over here. So we know this is plus minus root 3, and we can say that that the values of x, where f of x is less than 0, is from minus root 3 to positive root 3. So from a negative square root of 3 to positive square root of 3, and then we can just write it here, and it's not including any one of them because over here we're not including, so we're not including there. And what we get is that x is an element from not including negative square root of 3 to not including positive square root of 3. And that's the answer. And then if you just read it out like plain English, if you read out this statement in plain English, it'll be much easier to understand than thinking about it mathematically. We're asking where is the output of the function, where is the output of the function less than 0? When you look at the graph, it's easy to find. And we can do one more with 2 functions now, and then we can end off this video. So you have one, we'll leave this as the same function, but we'll add in one more function, g of x equals 5 times 2 to the x plus 7. And we want to ask for which values of x is f of x greater than g of x. Now this looks daunting. This is scary. Because what you need to do here is you need to find, what they give this to you. Okay, I think we can try this question, but don't expect the question with an exponential, because I think it's hard to solve for x as an exponent as in, yeah. So we'll use this using a graph, but don't expect the question like this. Don't expect an exponential. It'll probably be another parabola or a straight line graph. It won't be an exponential. But because we have the graph program here, then we can do it. And so the one graph is the same. Oh, and we can just change the a to b. We can just change it to b. A is nothing, and then b is negative 3. B is negative 3. And then for this graph, it was, I can put it back in, a was 5, c was 2, the x was at the exponent. What? No. And b was 7. Now we're asking, and we want to draw both graphs so that you can see it. Let's just zoom out a bit. Where's the second graph? Oh, that's a hectic graph there. Okay, so now we're asking, where does f of x, where is f of x greater than g of x? So where is the output of this, of the parabola, greater than the output of g of x. So well, we can see that from this point here, g of x is bigger. No, never mind. Can we see here, this is where f of x comes in. This is where f of x comes in. Let's just label them as f of x and g of x. It's much. F of x and then g of x. Okay. Same thing, just better labeled. So we can see that f of x comes in from here. So before this intercept point here, f of x was bigger. Can you see f of x was bigger here? And the more we zoom out, we can see that f of x is always bigger before that point there. And after this point here, and we're looking with respect to the x. So we can see here, f of x is still bigger. You can see it doesn't even appear on the graph. Here, f of x is bigger. Here, f of x is bigger. Here, f of x is bigger. At this point, f of x is still bigger because it's still above it. And then only at this point, at this x point of here, we can look here, it says negative 3.162. Only at this point here are they equal. And then after this point here, they stop being equal. And what we get is that after this point here, let's say at negative 2, f of x is less than g of x. And then let's say at 0, f of x is much less than g of x. And even at this point here, the same like before, only f of x is visible at 2, which means that g of x is probably greater than it. And even at 4, g of x is still probably greater than it, because it's not visible. And the more we zoom out, we can see that g of x is always, oh, that's zooming in. The more we zoom out, we can still see that g of x is always bigger than f of x, and there will never be another point where f of x and g of x cross, because of g of x's exponential nature. And now, since we've concluded this is the only point where they cross, and that everything before this point, f of x was bigger, we can now write, let's just take another point, it's negative 3.162. And what we can say is that, nope. What we can say is that this is the point, dx, so we can say that x is an element of this point not including, because it's not including there, so it's not including. Actually, never mind, that's wrong. It's x is an element from negative infinity all the way to this point not including. And yep, this was pretty complicated. And to figure out this point, we're going to have to use a simultaneous equation between both of these. And it's I think it's too complicated to do a simultaneous equation with x in the exponent. So you won't get one of these, you'll probably get one with, probably get a straight line graph like this. I say we can try this graph out just to try doing the, just to try get the simultaneous equation going. So now we'll try finding where g of x is greater or equal to the f of x. And we can do this by hand without looking at a graph, no graphs to help us. We can look at the end just to see if we're right. So we first have to find the intercepts. So what we can find is, we can just let them equal to each other. X squared minus 3 equals 5x plus 7. Bring the negative 3 over that side, bring the 5x over this side, we get x squared minus 5x, or never mind, x squared minus 5x equals 10. Because we brought 3 over that side. We can factorize out an x. So we know that, I'll do it over here, this top is still inside, x equals 0 because of this, or x, oh, never mind, we want to let it equal 0. I don't know if that's possible. I should have picked much better numbers. Yep, we'll retry that, because this is going to give you irrational roots, and you don't know looking at that. Okay, so instead of making it 5x plus 7, we can make it, let's say, x squared minus x squared minus 3x plus minus, doing this in my head, minus 5. Let's try that. I think this might work. Let's make them equal to each other. X squared minus 3 equals 3x minus 5. We'll say x squared minus 3x. Nope, I want this to be negative. X squared plus 3x equals, bring the negative half of it as well. So we get positive 5, which means this is positive 2 equals 0. Now this we can factorize. And what do we get? We get x plus 2, x plus 1, and we can FOIL out x times x squared, x times 1 gives us x, 2x times x gives us 2x, 2x plus x gives us 3x, 2 times 1 gives us 2, left with 2, you can say this equals 0, and we can say our two roots are x equals negative 2 or x equals negative 1. Now we know these are our two roots. What we also know is that we have a parabola here. So what can we say? We know that it's a positive parabola as well, which means that we can assume that the graph looks, with this is a negative graph here, and this is a positive parabola here, which means that this something goes like something like that, and the parabola goes something like this. Means we can assume that this point here is x equals negative 2, and this point here is x equals negative 1, which means that where is g of x greater than f of x? Only, well, here, at this point here, above this negative 2, less than negative 2, g of x, f of x is bigger, because the parabola is above. At negative 2, they're equal. At negative 2, they're equal, that's important. Above negative 2 and below negative 1, g of x is bigger, that's important. And at negative 1, they're equal, that's also important. And then above negative 1, f of x is now bigger, and that's not important anymore. So we can then conclude that this over here leaves us with x as an element going from negative 2 including to negative 1 including. And that is the answer we get. Oh, it's off. X is an element from negative 2 including to negative 1 including. There we go. And that's the answer. And that was the live stream. I'm done here. Thank you for watching. This is going to get uploaded. And see ya. Yep. Now I'm done.